Recording's rolling. It is Monday, November 10th. But you guys just turned in your energy quiz. Thank you for turning in your energy quiz. I will get those graded as soon as I can. So we're starting a whole new topic today, whole new unit, which is going to be on momentum. So all these blue banner posters. So my plan today is really just to go through these, which covers pretty much all the classic questions that I see every year pop up related to momentum. So we do that. Okay, so we have these well, momentum is mass times velocity. Momentum is conserved. Sum of momentum before a collision equals sum of momentum after a collision. Whenever you see collisions in physics, you should think these from context of momentum. Right? And then there's what's called this impulse formula. Right? So if you have mass times change in velocity, so how would something change velocity, which implies an acceleration? Well, there have to be a force. So some average force times some time interval. Right? So those are the main equations. They're going to branch off to a bunch of other ideas. Right? I did open your guys' next AP classroom, which right now I have the due date set to next Monday, so it's 7 days from now. I think by the end of this week, you guys should know enough physics to be able to answer those questions. Then I want to debrief that with you guys next week. Of course, there's no school tomorrow, so you guys have a good Veterans Day tomorrow. So you guys good so far with the agenda? What's going on? Yeah. Okay. So again, we're starting a whole new unit by AP's book. Well, this year anyway, they're calling this unit 4, I think. The 4. So what do you got here? Momentum. So if something has a mass and a velocity. Okay, guys, everybody look here. Look here. Pay close attention. This whole brand new stuff. Do you see how I have a arrow above the V? Okay, what does that mean?
The direction.
It means it has a direction. Right. So it means it's a vector value. It has both magnitude and a direction. So guys, look at this expression right here. Mass times velocity is what do you guys think P stands for? Momentum. Yeah, so lowercase p in physics, and it is lowercase. Guys, look here. Use that. So it is important that it has a direction. Now, mass is a scalar. That's why I didn't put the arrow above mass, but I did above the velocity and momentum. Oh, so something's going left versus right. Guys, does left versus right matter now?
Yeah.
Like if something's going to right, can add positive momentum, but left would be negative momentum?
No.
Yes, it would be. Okay. Now, that has not mattered for the past couple of weeks because energy was a scalar, so you could just add everything up. But momentum, if it's going left to right, you do have to consider is it negative or positive. So this is a vector value. It is conserved, so you cannot create or destroy momentum. A lot like you cannot create or destroy energy. All right, so that's a similar concept to last week. Okay, and it's involved in collision physics. Anytime you see collisions, you're thinking in terms of this. Okay, so everybody good with that so far? Mm-hmm. Hey, yeah, I'm not normally in the habit of throwing a bunch of arrow vectors over all the variables that are vectors, but for some reason when we get to momentum, it's like my brain just switches and I start putting arrows over all the vectors. So, all right, we'll go with that. Okay. So, closed and open systems. Well, this looks familiar too. Do you guys remember for conservation of energy, energy was conserved, but if no, that was a closed system. If there was an open system, you could do work on the system or by the system and add or subtract energy. So, very similar concept here. If you have a closed system, so there's no external forces, is another way to say that, then the momentum in that system is conserved. The sum of momentum before and after the collision equates. Right? But if you consider an open system so that there is an external force, then you can have a changing momentum. And my classic example for this open system is you hit a baseball with a baseball bat, and you're just focused on the ball. So if you're only focused on the ball, maybe the ball comes in with some mass times velocity, and then bam, you hit it with the bat, and then it changes what it's doing and it flies into the outfield with a different momentum. Something like that. If you're just focused on the ball, that could be an open system with the external force from the bat. Yeah.
Wait, what does P stand for?
Guys, what does lowercase p stand for?
Momentum.
Momentum. There you go. It was product of mass and velocity. There you go. All right. So you guys good? Good. All right. Now, thank you for momentum. Okay. Now, talking about collisions here. So anytime you see a collision, you're thinking about momentum. So let's look at just a classic collision just along an x-axis. So we're just going to mostly stay in one dimension anyway, but for most of these posters. So you guys see this all along the x-axis. Suppose you had some mass times velocity this way, mass times velocity this way, and then bam, they collide. Now, there's a lot of different type of collisions that could result. Like, do two objects stick together? Maybe do two objects bounce off each other, boing, or half deflated tennis balls, something like that. Like, any of those are possible. But regardless of what type of collision it is, this statement right here is always 100% of the time true. And that's that momentum is conserved. So, again, as long as you have a closed system. Right? So, mass times velocity is the same before and after. Right? Guys, how about this? I want to make up some crazy example. What if you had 10 units of momentum to the right and 10 units of momentum to the left? How much total momentum is in that system?
Zero.
Zero. It is because it would
It's like
track out. Vectors. Yeah, sure. Yeah, vectors, right? Yeah, because momentum is a vector.
Like 10%.
How about this? Guys, if there was zero momentum before, then post collision, how much total momentum is there in the system? Still zero. Yeah, there was zero before. There must be zero after because it's a closed system. Okay, so maybe you have like, well, I don't know, like 4 units to the left and 4 units to the right, or whatever the numbers are. But it would have to zero out after if it's zeroed out before. Okay, or maybe it doesn't zero out. Maybe there's overall more momentum to the right than the left. Because what if you have 12 to the right and 10 to the left? What's 12 minus 10? That'd be 2. Let's say afterwards you have 6 to the right. What do you have to the left? 4. Because guys, what's 6 minus 4? 2. Just like 12 minus 10 was 2. You guys get that? Right. Okay. So here's a more granular version of the setup. So sum of momentum before equals sum of momentum after collision. So if you add all the mass times velocity that's before and after, it has to equate. Right? Keeping in mind, of course, velocities might be positive to the right or negative to the left, and you have to also consider that in the calculator. That's good. Here too, I wanted to at least put one paper in your hand, so I just give you guys this. I'm not going to go through these today, but I do want to kind of point out kind of how to read this. Right. So these are all some very fundamental examples for how it's all momentum. So I have a general conservation momentum here. So if you wanted to try your hand at these to say, okay, am I really plugging the numbers correctly to make this work? You can always try here, right? I have different kinds of collisions. I have some other kind of questions, and at the end, I have a couple of impulse questions. Yeah. Okay, guys. What is momentum? How do you read this? Momentum equals what?
Mass velocity.
Mass times velocity. Yeah. So if something has a mass and has a velocity, you multiply it. Good. That's it.
But like, what's like the scientific way to define it, like in a more abstract way?
Okay. So here, I'll do an example with you guys. So let's say I got this object flying through space. Got this object flying through space. I got momentum equals mass times velocity. Now let's say this object has a mass of like 3 kilograms. Let's say it's flying in the forward direction at 7 meters per second. Makes that up. How much momentum would that be?
21.
21 units. And it'd be a kilogram meter per second. Unit of momentum does not have a special name or a special symbol. It's just kilogram meter per second. Okay. All right, so you guys get that? 3 times 7, 21. Yeah, that's it. That's it. If it's collided with something else, all right, then yeah, but here, if this has like negative 10 units momentum, then guys, what's 21 plus negative 10? 11. So there would be 11 units of momentum in the system. That would be true before and after the collision. So there would always be that much momentum in the system. Oh, okay, yeah. Okay, guys, where momentum is really useful is anytime there's a collision. Right? Anytime you see things colliding, you have to use conservation momentum because other methods will fail you. And if you try to do conservation energy, it falls apart unless it's elastic, but you don't get very many of those. Okay. All right. So we got this. Okay. Now, I'm saying that you could have all different kind of collisions. Maybe 2 objects could collide and stick, or collide and bounce off each other. Let's look at the collide and stick case. Because if 2 objects collide and stick together, which maybe has something to do with their material properties, right? Sometimes we'll say like 2 objects are made out of wet clay or something like that. They stick together. Guys, if they stick together, don't they have a common final velocity? Look at that. Look at this momentum equation here. So it starts off before, just like the regular general case. Got mass times velocity plus mass times velocity for the individual bits. Then we stick together to make one giant mass. Do one common final velocity, just like that. Yeah. Right. Or you can factor this out. But if you kind of compare and contrast here, right? So really similar looking expression, just post collision, they stick together. That's all. Right. That's all right. Right. And so this is one extreme kind of condition that you could have. One kind of extreme collision you could have is where they stick together. There will be an example later today where you see a bullet embed itself in a wooden block. And that would also be an example of those too, right? Fire a bullet into a block. Right. Now, at the extreme other example end of the spectrum of kind of collisions you can have is what's called perfectly elastic. This is perfectly bouncy. Right? And in physics, what marks something perfectly bouncy are these 2 green equations right here to make the system of equations. So yes, momentum is conserved, although that's true for all collisions anyway. But here's your special condition, is that Ooh, guys, what is this? Kinetic energy. So kinetic energy also happens to be conserved, again, only for the special kind of collision. And I'll give you guys an example, or as close to a really example as I can give you. That's Newton's cradle. Okay, you guys see that? So this is showing both conservation of momentum, but also conservation of energy, because these balls are pretty well perfectly bouncy, or as bouncy as they could possibly be. If I narrow it down to 2, because a lot of times in physics will just narrow it down to 2. Look at that. Okay, you guys see that? Good there? Right. Right, or however you want to balance these. Right, to do 2 times. Okay. Okay, so if there was no energy dissipation, then that could bounce forever. Okay, you guys get that? Now, so how do you solve those system equations? Like, here, if I told you what the masses were, suppose I told you the masses, and I told you the initial velocities, so like got two objects, say, headed toward each other, for example. Okay. You know their masses, you know their initial velocities, and I also told you this condition. I say, oh yeah, by the way, this is going to be perfectly elastic, perfectly bouncy. Do you think at that moment there would be enough information in the system where you could, in theory, calculate the post-collision velocities? You could? Okay. Yes, there would be. And actually, you're looking at it right here. This right here is the solution to the system equations in this gold box. It's this really funny looking fraction. Okay? But this is the the solution to the system of equations of these green two. Right? Now, what can you do with this, or what would I expect you to do with this in this class? I'm not going to expect you to memorize this. Okay. And in AP, they rarely ever ask elastic collision questions. I've seen them ask kind of two categories of questions, just very rarely ever in the past. And I'll tell you what they are. Right? So one situation I've seen them bring in perfectly elastic is as part of a larger question where they have just a very simple scenario. So for example, like this, what if you have these two balls have the same mass, one starts at rest, and one of them, maybe I lift up to like on top of the hill and I let it go down to the bottom of the hill. Okay? And then maybe it collides with this one and then sends this one off the edge as a projectile. I've seen that exact question before. Okay? So you have to navigate, well, what do I do with this elastic collision in the middle? And you can see it pointing right there. You guys tell exactly what just happened. Okay, thank you. You guys tell what just happened? Is that one ball came down and collided with the other, and it transferred all its momentum to the other, pointing just like that. Okay. Now that'll only work if those two balls have the same mass as each other, and also one starts at rest. You guys get that? One just very simply transfers all its mass and energy to the other one. Okay. Which also you can show mathematically with all this math right here. Okay. Okay. And the other case where I've seen AP ask a question regarding this kind of collision is in a multiple choice context. They'll have two objects collide, and they'll give you multiple choice answers, and they'll say, which of these multiple choice options displays a perfectly elastic collision? And I think the fastest way to handle that would just be go through the choices one by one, like start with A and then B and C and D, and just run the numbers with these two equations and see which one satisfies both conditions. A lot of times they'll both satisfy the first condition, but which one especially satisfies this other condition, this kinetic energy condition? Right, you guys get that? Okay. Or if you want to, you could just memorize this gold box. Right? Okay, you could do that too. Right? I'm not going to expect you guys to memorize the gold box, but you could. All right, so let's look big picture here. Big picture. I got this whole spectrum of collisions. And so perfectly elastic, that's one you just saw where they bounce off each other. At the other end of the spectrum is perfectly inelastic where they collide and stick. And do you guys think that realistically in the real world, usually you end up somewhere in the middle, like two half-inflated tennis balls, kind of boing, bounce not very well? Yeah, so here's general. No. Right. And okay, so I give you a picture for each one of these conditions. What's happening in terms of momentum in this column? What's happening in terms of kinetic energy in this column? Okay, so let's go through. Okay. So perfectly elastic. Momentum is conserved, of course. But kinetic energy is also conserved for this very special kind of collision. You guys just saw that. Okay. How about a general case? Well, okay, momentum is conserved also for collision. Okay. And kinetic energy usually does what? Post-collision. Decrease. Decrease, right? Now, guys, does that energy disappear from the universe? No. Where do you take a guess? Where do you think it sort of goes to? Yeah, thermal, heat. Sometimes I see the phrase permanent deformation. That's a common thing, right? Two balls like fly down, kind of smash each other. Right? Yeah, I bet if you measure the temperature, they go up a little bit. Right? But those are non-mechanical forms of energy. So in this class, Physics 1, it's really hard to account for that. That's why we're not usually doing energy. We're looking at collisions in terms of energy. We're analyzing it all in terms of momentum, which is very simply conserved. Now, perfectly inelastic, they do collide and stick, and lo and behold, momentum is conserved again. And guys, anytime two objects collide and stick, Guess what happens to kinetic energy 100% of the time? It has to decrease. It has to decrease. Right? Because you can make up any masses, you can make up any velocities. And if you have them collide and stick together, I can guarantee you, I've never seen a counterexample, I can guarantee you the kinetic energy will always decrease. Okay. Okay. Finally, explosion. Hey, what if you had a grenade lying around and the grenade just pow, exploded? Maybe explodes into 2 pieces, maybe explodes into 100 pieces. The physics is the same. Momentum is conserved. So, guys, if the grenade was just sitting there on the ground, it just like pow explodes, and now you got 2 grenade pieces. Right? Guess what happens to the center of mass of that grenade system if it was just starting at rest?
Stays there.
Stays exactly there. It never moves. The center of mass never moves. Momentum is conserved. What if you do this? What if you take a grenade, throw it through the air, and it explodes, pow, midair? Right. Guess where the center of mass stays for the 2 grenade parts? It's as if the grenade never exploded at all. It never changes what it's doing. Actually, I have a poster just for that. So momentum's still conserved. But what's happening in terms of kinetic energy? Oh, guys, if the grenade explodes, what happens to kinetic energy in the system? Increase. Yeah. Right. Now, did that energy come from somewhere?
Yeah.
Yeah, I think there was some. Exactly. Yeah, they stored in the gunpowder, or like that. That phrasing, stored in the gunpowder, or some kind of chemical bonds, right? And so maybe chemical energy converted into mechanical energy. Okay, you guys get that too? Okay. Well, listen, guys. What if you film and it's a grenade exploding? So you see it going through the air and explodes, and you film that, and then you run that film in reverse, and the 2 parts come together and hold it. Doesn't that just turn into a perfectly inelastic collision? Or vice versa. What if you had a perfectly inelastic collision and you run that in reverse? Doesn't that look like an explosion? Hey, aren't these 2 just opposite processes of each other? I bet they are, and I bet mathematically it's just the exact same thing. These are exactly opposite processes. You guys see that? You guys good with all the different kind of collisions and explosions? Yes. All right, next one. Okay, so I do have a couple of labs queued up for you guys this week, and then maybe another one next week. Okay. That involve these collision carts. You guys remember these low friction collision carts? Of course, you can always change the mass of these by simply stacking on more lab weights. You can do that too. Okay. Now, I only have one here just for demo, but what if these are colliding with each other? They might bounce off each other, or I could tape on some of these magnets right here with masking tape and paper towels. Right? They can like stick together. Right? We can create different kinds of collisions. You guys get that? Right? So look for that. I'm just introducing ideas today, but look for that in the next few days. Okay. So here's a general collision table that you could account. What are you accounting for? Okay, so we got different trials. We got maybe a massive different carts. Right? Got that in kilograms. Now, here's the really tricky part. Guys, you're juggling 4 different velocities. You got the velocity for each cart pre-collision and the velocity for each cart post-collision. Right? You guys see that? Right. Now, maybe you could sort of simplify this down. Like if one cart starts from rest, one of these columns could just be 0. Okay. But you're still juggling a bunch of different velocities, right? So just maybe take the next couple days. How can I maybe do that? Okay. I'll give you guys some speed gates. One trick I teach in the past when we had this idea was to take a glue stick. Here, I got this little stamp right here. And to masking tape the glue stick here. And as this goes through the speed gate, maybe you can read a velocity value, like a speed value, something like that. Okay. And then, can you guys calculate the momentum before and after by doing mass times velocity before plus mass velocity before? That could give you the total momentum before the collision and then after the collision. Now, guys, momentum before and after, do you think those 2 numbers are about the same? Like if this is 5.5 kilogram meter per second, I bet this is pretty close to 5.5 kilogram meter per second, or it should be. That's what I'm claiming. Right? And what do you think generally happens to kinetic energy? Well, yeah, it should either decrease. It'll definitely decrease if they stick together. Right? If they bounce off each other, boing, relatively elastically.
It would decrease.
Yeah, maybe decrease a little bit or stay pretty close to the same, something like that. But you guys can look for that. I mean, you can gather some empirical data and tell me if I'm telling you the truth here. Okay? Here's a little bit different lab table. Inelastic collisions. Okay, so this one where maybe I tape magnets on and they stick together. Did you guys see? It's consolidated a little bit. So here I have for one of my columns is just the final velocity of the 2 objects stuck together. You guys see that too? Right? So when you eventually do this one back in lab area, see that? Maybe some similar questions. What's the momentum before and after? What's the kinetic energy before and after? Right. And this one, the kinetic energy should always decrease. You can see that too. Let's try. You guys good there? Right. So I'm going to get a bit into the weeds here, but Here, got some bonus stuff for you guys. Okay, here's one of my bonus posters. If this is a little bit too much, you don't have to worry about this one. But if you want to know a little bit of extra, I've seen where I've seen this on the AP guys, look up here. Okay. I've seen on the AP grading rubrics for FRQs, they can award credit if a student is able to use this and use this. Is what's the relationship between kinetic energy and momentum? Right? You guys notice that these have the same ingredients? Because momentum is mass times velocity. You guys learned that today. Kinetic energy, isn't that 1/2 mv squared? Yeah, so it's the same ingredients, right? Something to do with mass, something to do with speed or velocity, right? So if you know the momentum, you can solve the kinetic energy, vice versa. And here's the connection. So I gave you guys a derivation over here, and it leads straight to this. So if you square the momentum, divide by double the mass, that tells you exactly what the kinetic energy is, right? So yeah, I guess if you have extra space in your mind, like, oh yeah, I can learn an extra thing that can maybe use it in an FRQ, then this would be an extra detail, right? When we get to rotational physics, probably in December, there's an analogous rotational formula. This is rotational angular momentum, or angular momentum, I should say, is L, and then rotational inertia is I, right? So there's way to do that too. All right, so that's just a little bonus right there. This next one is also sort of a bonus, but I want to do a lab with you guys that involves this. And the question this one addresses with coefficient restitution is how bouncy is a collision? Okay, so here, give you guys some examples. You guys see this bouncy ball right here? Okay, watch this off the paper. Oh, okay, it's kind of bouncy off the paper. How about off the wood? Ooh, that's even bouncier off the wood. And that Newton's cradle I showed you guys was nearly perfectly elastic itself. Ooh, what about this one? What do you think this one's gonna do? That didn't melt at all. It looks like perfectly elastic. The table surface. Right? So how can I quantify this type of collision? Or what if I have something in the middle, like I have to play a tennis ball? It's like, right? Okay. So the way in physics you quantify this, it's called coefficient of restitution, is you take the difference in velocities post-collision and compare that to the difference of velocities pre-collision. You guys see that? Right? So post-collision difference of velocity, the delta here means a difference in. Okay, sometimes it needs change in. This time it means difference in. So you subtract these two, and divide those differences. Right? You guys have that? Now, because in a collision, normally something reverses direction. Naturally, this would always come out to a negative number. These guys look really close because they did something really sneaky here. Guys, watch this. Okay. You guys see on the top, it's final minus final, bottom is initial minus initial. That's all good. Right? But, guys, come here. On the top, it's B minus A. And on the bottom, it's object A minus object B. You see how I reverse that? Right? And the reason I did that is because if you didn't do that, this would always come out to be negative. But because I reversed one of these, it naturally comes out positive. Alternatively, you can just take the absolute value. So this will always come out to be a positive value. Okay? Now, see if you guys can figure this out. You guys ready to do some critical thinking? This number, this coefficient, is always bounded between something and something. What do you guys think? It's bounded between what and what? 0 and 1? Yeah, that ends up being the answer. Because if two objects collide and stick, well, if they're stuck together, what's their post-collision difference in velocities? 0. And then it doesn't matter how fast they were headed toward each other. 0 divided by anything would be 0. So that's one boundary condition. Right? And the other extreme collision you have could be boing, perfectly bouncy, like Newton's cradle. In which case the difference exactly reverses. So maybe you have like 17 divided by 17. And that would give you 1. You guys get that? So this is always bounded between 0 and 1. Okay? Now there's an alternate way to find coefficient restitution. Sort of a special condition. That's what if you bounce the ball off the floor? And your two objects could be the ball and the earth. It does have to do with material properties. So maybe ball and the earth, where the earth is considered like surfaced by a tile floor. Okay? So this is a good lab that maybe I'll try to fit in next week. Okay? Now, if the earth is basically not moving in this case, then wouldn't the difference in velocity between the ball and the earth just be represented by the velocity of the ball? Because you'd just be subtracting 0, right? So another way to say this is, what's the rebound speed, like this ball leaving the floor, compared to the crash speed when the ball is about to hit the floor? Because that would also tell you coefficient of restitution. You guys get that? Okay. And you can solve that with nothing but a meter stick. So as your only measuring tool. So what if you take a tennis ball, you drop the tennis ball from, 100 centimeters, and it rebounds to boing, like 65 centimeters. Do you think there's enough information there you could figure out how bouncy is the ball on the floor? Yeah. Okay. So let's go back to a couple of weeks ago. Hey, guys, does this expression look familiar? So,
Yeah, it does.
so crash speed could be square root 2gh. from its drop height. Isn't that the Galileo question? Right. You guys saw that like at least 10 different times in the past couple weeks. And then the rebound speed, you can sort of do the same thing. It's just based off this rebound height. Now, if I want to know the ratio of these speeds, I can very simply take the ratio of these square roots. And some stuff is going to cancel out. Guess what cancels out when you divide this by this? How about the 2G? Guess that? 2G is going to cancel? So if I took this up to Mars and I brought the same tile floor with me. Okay, so would this rebound to the same height on Mars? Yeah, it's equally bouncy. I bet it does. Bet it does. Okay. So it ends up being this expression right here, square root of the ratio of the heights. Right, you guys good? Right. So AP is not going to ask this question, but I'll give you guys a lab on it because it's a fun lab. Oh, in fact, there's a good lab table for it right there. You just measure with the meter stick. All right. Okay, so let's get. So we've been off the beaten track for a few posters. Let's get back on track here because here's a really important concept, guys. You're going to see this all over the place on the AP exam. Something called impulse. Right. So what is impulse? What does that have to do with this graph or this bat and this ball? Right. So impulse is very simply a change in momentum. Right. Now, guys, if there's a change in momentum, are we talking about a closed or an open system? Yeah, it's got to be open, right? In this case, maybe I'm just focused on the ball, right? Because there's a changing momentum, right? It's got to be an open system. Right? So, that could be, hey, how about a massive change of velocity? So, normally the object keeps its mass, the mass doesn't change. So all the change is routed into change of velocity, right? Now, how do you get that? You get that by applying a force for a time interval. So I'll say like an average force for a time interval. You guys that? Okay. And on a graph that shows up on a set of axes that's force versus time. Hey, does that look kind of familiar to something a little bit different from last couple weeks? Guess what graph did you guys see last couple of weeks? It wasn't force versus time. It was force versus what? Distance. Okay. And guys, what did the area, going back to like a week or two ago, what did the area under force versus distance tell you? Work. Which was like a transfer of energy. This is a very similar concept. In fact, it could apply to the same scenario if you just think about it a little bit differently. This is force versus time. And I'm telling you guys that under the accumulated area under that curve is this impulse. Right? So suppose this ball is coming in, and you know the mass of the ball, and you know the velocity of the ball, say like to the left. So you got some negative momentum, right? And you hit the ball with a bat, with some force for some time. Could you apply that impulse and then figure out the final velocity of the ball and then figure out like where it's going to land in the outfield, something like that? Okay, see, you could all put together. Right? So let's look at this graph then. So realistically, how this graph normally works is if you film this in slow motion, here it might look something like this. So here comes this ball against this bat, right? And then at some point, I'm going slow motion. I'm going frame by frame, like frame by frame by frame. The ball makes contact with the bat, and then it pushes harder and harder and harder against the bat, and then it starts to rebound away from the bat. And then it finally leaves the bat. Couldn't that be like several frames? Right? It might be over like 1/100th of a second with a slow motion video. Right? Could you guys imagine that? Okay. And so oftentimes with this force versus time graph, this time interval might only be like a fraction of a second, maybe like 1/100th of a second. It doesn't have to be. It could be longer than that. But oftentimes it is. Okay? And that's where this triangle shape is coming from. Okay, so here's the ball making contact with the bat. Then it's pushing maximally against the bat right here. And then now it's reversing direction, and then it leaves contact with the bat right here. And so these graphs oftentimes make these triangle shapes. Okay? So could you find the area of the triangle? Call that impulse. Right. Now, if you want to feed this into this equation, notice, what kind of force am I calling this? I'm calling this a what force? An average force. Right? Let me tell you guys about averages. How many of you guys are taking calculus right now? Taking calculus, right? So probably next semester, you guys are going to get into average value. And the way you find average value is to find the area of the shape, which is going to, well, in calculus, it's called integration, right? Which is, you guys have definitely been doing derivatives, right? Right. So it's just the opposite process of derivative. If you just do a derivative opposite, backwards, it'll accumulate the area under some curve. It's called integration, right? What if this was an iceberg? Can you guys see my iceberg right here? Yeah. I'm going to plot my iceberg inside some aquarium wall. So I'm going to lock it off, the left side, the right side of this aquarium. I'm going to let that iceberg melt. Doesn't it melt down to right about there? You see it? And that right there is the average value. So in math terms, what you do is you find the total area, you divide by the base, and that gives you the average height, which now looks like a rectangle, doesn't it? Yeah. Right? And that's the number that would feed in right here. So average, guys, is average force the same thing as maximum force? No. Right? In fact, if you have this exact geometry, here, I'm gonna throw some numbers at you guys. Suppose this average force was like 7 newtons. Average force is 7 newtons. Take a guess. What do you think maximum force would be? 14. Ah. Suppose you had a baseball and it can handle up to like 10 newtons of force. Anything over 10 newtons, the seams are going to bust. And you say, oh, the average force is only 7 newtons. Is the baseball safe?
Yes. No.
Probably not, because I bet the maximum is closer to 14. Ah, yes, yeah. All right. Did that. Okay. This one, well, this is a good conceptual one. Okay? Suppose I fire a couple of objects at this bowling ball. The bowling ball is just sitting at rest. Okay? And one object is going to collide and stick, maybe represented by this bullet that can embed in the bowling ball. The other object is going to bounce off the ball. Which of these cases, and they will be different, which case do you think gets the bowling ball rolling off faster to the right?
To the bottom.
Bowling.
Huh. Okay, I'm hearing one of each. Let me see show of hands. How many of you guys think that the inelastic case on the top would get the bowling ball rolling faster? How many of you guys think the more elastic case in the bottom would get it rolling faster? Okay, so you can see about half and half. Okay. Let me try to convince you guys that the elastic case will get it rolling faster. Okay. So let's throw some numbers. Suppose this bullet comes in with like 10 units of momentum. You guys see it coming in? Maximum velocity is like 10 units. Okay. And it embeds in the bowling ball. Now, don't these two objects together have like 10 units of momentum? Yeah, or it just rolls off with 10 units of momentum. Okay. But if it bounces off the point, suppose it comes in with 10 units of momentum, then it bounces off the other way with like 7 units of momentum to the left. What's the difference between 10 to the right and 7 to the left? And don't say 3.
17.
17. Ah! Okay, you guys get that? 17? So how much momentum was just transferred into the bowling ball? 17 units, which is maybe almost twice as much as the original case. Ah, you see that? The bowling ball gets rolling up to twice as fast. Or something like that. Yeah, disregarding the mass of the bullet itself, which could further slow it down too. So that'd be another reason. Right, guys good? Ooh, this next question. This is one of my favorites. This very specific question, but it's called ballistic pendulum. So the scenario that the story that might go is this is, let's say you go back to like 1880. We got the new revolver. Hey, I wonder how fast this can fire. Right? How do you figure that out back in 1880? So what they do is they measure the mass of the bullet. They fire it into a block of also known mass. So they measure the mass of this block of wood, right? And they have this on a string of known length. And they just see how high does this swing up to. And at that point, there's enough information to be able to solve this if you know physics. Okay, so after that, it's a 2-part process mathematically. And I'm going to solve this backwards. So forwards in time, what happens is that the bullet embeds in the block. Does that sound like an inelastic collision? That's an inelastic collision. And then afterwards, the whole thing swings up to some height, right? But mathematically, you solve it backwards to solve the speed of the bullet. And there's variations on this question too, but I'm giving you guys like the main question you usually get. Right. So our goal is what's the speed of the bullet? Okay. Right. So hey, this is conservation of energy from last couple of weeks. So if you know this height change, could you figure out how fast the block was getting to go, like post collision with the bullet? Yeah. Okay, so we can chase down that speed, and no surprise, you square root 2gh. Right. Now, guys, could you solve for that h based on this L in this data? Right. Doesn't that look exactly backwards of, hey, look who's back, look who's back, it's this guy. Yeah, that's that. That's the same thing. You guys remember? How many of you guys remember that? How many of you guys remember that? Right. Yeah, look at all those hands. You guys remember that? This height is L1 minus cosine theta. Right? That could fit in here if I gave you all theta. You guys could figure that out, right? Okay, right. Now, remember what the speed means at this point. This is speed post-collision. So this is after the bullet has embedded itself in the block and then the whole thing swings up. I can do that conservation of energy all day. That's fine. You guys been doing that. But here's the new physics, is if you back up in time, reverse the film a little bit more, that bullet embedding itself in the block. Guys, if you guys got a bullet embedding itself in the block, does it have to push a bunch of wood fibers out of the way? Yeah. Do you think there's an enormous transfer of mechanical energy to like deforming those wood fibers, maybe heating up a little bit on the thermometer? Yeah. So you can't really use conservation of energy for that collision, but you can use conservation of momentum, because that's conserved. Okay? So mass times firing speed of the bullet. Ah, now we got something we can solve for. Is the combined mass, block plus bullet, times the post-collision velocity after it embeds. But guys, what's this velocity right here?
0.
Exactly. That's what we did up here. This is this. Yeah. See how that all fits together? So we're solving backward time, right? Once you got that, you just pop that in, and you got your answer. There's the firing speed of the bullet. Okay? Right, so I'll probably have you guys solve that sometime in the next couple of weeks. Okay, guys ready for that one? Okay, guys good? Okay, so then let's review that one also. Okay. All right, here's one you guys have seen before. Ball bounces off a wall. Okay. So let's say we're just focused on the ball. So open system consisting of bowling ball. Say it's coming in at 10 meters per second, straight left, and then boing rebounds 7 meters per second to the right. Who can tell me, guys, what's the change of velocity of that ball?
Yeah.
17, right? Because it'd be 7 minus -10. You guys get that? So the difference is 17, right? Yeah, okay, because it changes direction. Okay, so, I wonder what was the force from the wall to cause that to happen, right? And guys, does this kind of look like Newton's second law of motion? F equals ma. Isn't this acceleration right here? Change of velocity over change of time, right? So change of velocity could be 17 meters per second. The mass of the ball, maybe you measured that. And one more detail you'd have to be able to solve this is what is the time interval of that collision with the wall? Maybe a tiny fraction of a second, but you have to be given that. And then you could solve for what I'm calling the average net force. Yes, I do. Okay. But there's another way you can also get that equation. Guys, look really close to this. M delta V over delta T. Isn't that Newton's second law of motion? Okay. That's also this right here.
No.
It's the same thing. Can you just take this impulse formula, take this time interval, divide that over? It's the same thing. You see that? Right? So some physics teachers also teach that this impulse formula is Newton's second law of motion in disguise. This is just one algebra step removed. You just shuffle over the delta T and you got it. You guys see it's the same thing? Yeah, same thing. It's a good connection there. All right, you guys good? It's good?
Yeah.
Right. And then here's a two-dimensional version of those. Right. Now I have added some conditions to make this a little simpler. I'm going to call the wall frictionless, so I don't have to worry about any side forces or forces in this vertical axis, I guess. Right. And I also don't have to worry about any torques, which we haven't talked about yet. Anyway, right. I also made this an elastic collision so that this incoming speed and this outcoming speed actually maps each other. Okay. So we got all those conditions going on. Okay. And I think you guys have seen this one before. Okay. So guys, the force from the wall, isn't that what kind of force is this? No. Normal force. Yeah. Okay. Which means perpendicular to the wall, which means it's only strictly to the right. Okay. So all the change is happening along this x-axis. Is there any change that happens along this y-axis? No. Right. The ball just keeps on going. Right. For this very special set of conditions. Okay. So really, whatever this velocity is, don't I have to multiply it by sine theta to say, well, how much was it headed straight towards the wall? And down here, how much it's headed straight away from the wall? Right? And if it's perfectly elastic, very special case here, then that's where I'm getting the 2, as in the 2v sine theta. Okay? Great. Then multiply in the mass of the ball, divide by the time interval, that gives you the average net force, in this case, the normal force. Okay? You see that? All right. How about a general 2D collision? Okay. Now, AP does not really go into 2 dimensions so much, so I doubt they would ask this. But what if you see billiard balls? What if this red billiard ball strikes past this green other ball that's just sitting here? Okay. So the guiding principle is this: momentum is conserved along each axis. So, guys, as this red cue ball is coming in strictly to the right, is it moving up or down at all?
No.
No. So, is there any up or down momentum?
No.
There is not. How about post collision? Can there be any if I find the sum of the vertical momentum along the y-axis, does it still have to zero out? Yeah, because that would satisfy this condition here. So is this mass velocity strictly upward? Does that match this mass velocity strictly downward? Has to, because they have to zero out. Okay. Along the x-axis, this came in with some mv to the right. Now, if I break these down into components, because these are vector values, right, the momentum, does this red one have an mv to the right plus this green mv to the right? Does that add up to the original mv? Has to. That's this condition. Okay. If you go to college and they go into 2D collisions, another classic example is how about a car crash? Suppose there's a car coming straight north and a car coming straight east into an intersection. They bam, and then they move northeast together. Okay. Could you set up an inelastic collision? Okay. But these conditions would still apply. So the momentum in the north direction and the momentum in the east direction still have to be conserved before an actual collision. Okay. That's how you'd solve that. Okay. All right. These last 4 posters all kind of go together, and they're all focused on the center mass. You guys remember center mass? You guys seen this before? Right. So let me remind you guys what center mass is. It's just a weighted average of mass. So you do mass times location plus mass times location. You add up all the mass locations, divide by some masses, you get to do the average location. Here it is for 2 objects. That's okay, right? You guys got that? Now, with momentum, Ooh, guys, for momentum, do you think you could change this x to a v? Like take the rate change of location, call it velocity, and you can just sub in a v where you see the axis, right? Right. Actually, I think that's on your AP equations. They did list that down here. They say the average velocity for like the center mass velocity. It's the very bottom equation here. Right? It looks a lot like the center mass location here. But this one's for location and this one's for velocity. But otherwise, they're very nearly identical. You got that? Right. So how could that apply to all these collision examples? And I have 3 last posters for you guys. 3 last ones. So suppose out in deep space, you got these 2 asteroids and they collide. And let's say we're focused on the 2 asteroid system. So you're not focused necessarily on each individual asteroid, but the system as a whole. And I marked a little X for maybe the center masses. Okay. Now, guys, before collision and after collision, guess what happens to the center mass? Does it change what it's doing? Turns out, yeah, you're right. It does not. It does not change. So if I'm only focused on the center mass, okay, it moves here, moves here, moves here. Say, hey, when did the collision happen? I will never know if I only focus on the center mass. I never. Here, guys, everybody, listen to me, right? Because what I just told you is like guaranteed going to be an AP question in some context. I don't know how they're going to phrase it exactly, but that concept is going to show up. Okay, so I'll say it again. If you only focus on the center mass of the system, you never know when the collision happens. There's no way to know. Okay? And if that center mass happened to just be at rest and maybe the 2 asteroids head support each other, then again, regardless of what kind of collision, it could be elastic, they bounce off the point, could be inelastic, they stick, right? Could be in 1, 2, or 3 dimensions. You never know when that collision happened if you only focus on the center mass, because center mass never changes whatever it was doing. If it had a velocity, it maintains a velocity. If it was at rest, it remains at rest. Right? Here's a 2-dimensional example down here. Right, guys got that? Okay. How about this? What if you have an ice skater on an icy pond? So we're getting rid of the friction. You guys got that? Get rid of friction. This guy throws a snowball off to the left. And he scoots back to the right. Right? Do you guys think if everybody started at rest? So here's the center mass just hanging out right here at rest. Do you guys think the mass velocity of the ball to the left has matched mass times velocity of the skater going to the right? Yeah, because it all has to zero out. Yeah. And if you knew any 3 of these, could you solve for the 4th? Yeah. Okay, I have a good video examples for you guys for this one too. So, hang on, we'll come right back to this one. Okay. But I got one more poster. This is the last poster. Let's go back to grenade. Let's have an explosion. Have I been saying that an explosion is just the reverse of a collision? Yeah. So it's the exact same physics that apply. So what if you throw a grenade in the air and that grenade explodes into, let's say, 1 million parts? How? And you focus on the center mass of all those parts. Does the center mass land exactly down here as if it had never exploded at all?
Yeah.
Sure does. Sure does. Again, as long as you ignore air drag. Right? Here's probably a more likely question you could get. What if the grenade explodes into 2 parts? One part lands way downfield off to the right. Do you think the other one lands maybe kind of close to where it started? I've seen AP ask exactly that question too. Right? But the center mass never changes what it's doing. Right, guys good? Right, so to close off class, I've got one video demo for you guys, which is pretty much that poster right there. Right, so we take this here it is. I found it. We're taking a trip aboard the Magic School Bus. Oh yeah. Hey, look, they're on a frictionless field. You guys see that big old frictionless field? They're all just sliding around. Right? All sliding around. They got to get put in place by this big old bus crane. Otherwise, they'll just keep sliding because there's no way to stop because there's no friction. Right? So let's get this game going. And right. I'll probably show this to you guys also on Wednesday because my first class we didn't quite get to this. All right, building up suspense here. Guess we got 22 minutes of episode to fill. All right, and throw this ball. Throw the ball. All right, guys, what do you think is gonna happen? You know she's on a frictionless field, right? There's no friction. Yeah, you guys got that? Right? She throws the ball forwards. How's she gonna move?
Backwards.
Yeah. Oh, there she goes. She's off to second base. Right? Now, if you knew the mass of the ball and you knew her mass, now let's say you have a radar gun trained on the ball, so get the ball's going some speed towards the plate. Is there enough information at that point you could calculate how fast she's headed back towards second base? Right? And it's all right here. This is the same thing. because we know the mass of the ball, we know her mass. Maybe we measure the speed of the ball head towards the plate. You can calculate this right here. Her head back for second base. It's all right there because she started at rest on the mound. So the sum of momentum has to be 0, and everything else applies. Guess that? All right. So that is our pause point today.